Hello students, welcome back. So far in lesson 0, we reviewed selected topics from pre-algebra and basic algebra, and then from intermediate algebra, or fundamentals of algebra, whatever you may want to call. Now let us spend some time on advanced algebra, or college algebra, STEM algebra, business algebra, algebra for teachers, whatever the name. There's so many algebras in college level. In any case, here, at this level, the focus of attention is the inequality. How do we deal with inequalities? By the way, in the review of intermediate algebra, our focus of attention was equations. Remember? Equations and then factorizations, those kind of things. Now, equations equal to 0 versus inequalities. Which is easier? Which is harder? Of course, inequalities are harder, so that's a bit advanced. Let's talk about that. Let's begin with some terminologies. If you have a polynomial expression like that, and this expression has k zeros, c1, c2, c3, all the way over to ck, because they are k factors, k linear factors, excuse me. That is because if you set this one equal to 0, you see, f of x is equal to 0, so set this one equal to 0. That means either first factor is 0, or the second factor is 0, or the third factor is 0, or in the end, the last factor equal to 0. One of them has to be 0 because if I multiply a bunch of non-zero factors, I'm not going to get 0. I'll never get 0 that way. So these are the zeros of those polynomial expression, c1, c2, c3, and so on. Now, for each 0, look at these powers. m1, m2, m3, and so on. Those are called the multiplicities. So the first 0 is c1 with multiplicity of m1. The second 0 is c2 with multiplicity of m2, and so on. This is the last one. X equal to ck with multiplicity of mk. Now, why are these multiplicities so important? We're going to focus upon whether a multiplicity is even or odd. Because, roughly speaking, what's happening around each 0 is whether we have sign change or not. And that is equivalent to, roughly speaking, multiplying by -1 to the m power. If the power is odd, then you're multiplying by -1, so we have a sign change. If the power, the multiplicity, is even, then -1 to the even power is just +1, so we have no change. You usually start from the biggest 0, and when x is really, really big, or going to infinity, then this whole expression is going to be greater than 0 if this leading coefficient is positive. If this leading coefficient is negative, then negative times something really big, so we're going to go down to -infinity. So in any case, that's where we're going to begin. And then we have to consider each 0. Let's go through those with an example problem. And here is an example of very, very simple inequality, as a matter of fact. It's a quadratic inequality. So how do we work it out? I see this kind of answer a lot. Factor it, and this is the very same expression that I introduced you before. This expression here, and I'm just recycling that factorization over and over again. So here you go. And then from here, I see this a lot. So that we have that, and you just earned an automatic 0 credit. Now your job is to figure out what went wrong. I mean, I explicitly said so far so good, so there's nothing wrong here. Now what happened here so that you ended up with a 0 credit? Well, if all these are equations equal to 0, all these had been equal to 0, this would have been perfect. Why? Because A times B is equal to 0. That means either A is 0 or B is 0. So either this one is 0 or that one is 0. Now, what do we have here? A times B is less than 0. Does that mean either A is less than 0 or B less than 0? No, that is not the case. If both are less than 0, then the product is positive. Completely different situation. How do you make it right? One way to do that is to draw a graph like this. So this is quadratic expression, so it's a quadratic function. So I plot this function, and y-coordinate is a function value, and that's less than 0. So y-coordinate is less than 0. We have down below here. So down below, -2 to this number, that'll turn out to be -2 to 2/5, as you saw from the factorization. And that's one way to handle it. But this doesn't work very well if your function is really complicated, especially when you have rational function. Or even worse, if you have radicals flying around. So here's a second solution, which I'm going to emphasize. Factor it, and then we get that. That's the original expression. Wait a minute. Oh yeah, less than or equal to 0. Less than or equal to 0. Okay, all right. Nothing from there. And then we have two zeros, x equal to -2 and x equal to 2/5. And then what are the multiplicities? They're both 1. Nothing is here. Nothing is there. So 1 is hidden for both cases. So they're both odd multiplicities. So when x value is really large, from here in this interval, this whole expression will be positive. If you plug in x as, say, 1,000 or something like that, very positive times another very positive. So this will be positive. Now, when I cross this 2/5, I have to have a sign change because we have an odd multiplicity here. And then when I cross this 0 again, I have to change sign because this one now has odd multiplicity. What is the behavior of even versus odd multiplicities? Roughly speaking, if I'm crossing from here to there, I have sign change in the x-coordinate in this whole expression, and then that to the odd power. So okay, we have sign change because negative to the odd power is negative. But if you have even power, negative to the even power doesn't change, so stay the same. So that's how this thing is working. And of course, if you cross-check with your graph, you're going to see that more explicitly. Let's see. Let me copy and paste this graph. So at this point here, to my right, the graph is behaving very much like a line locally, a linear function, because we have 1 power over there. And here, again, graph is behaving very much like a linear function, a line, locally at least, because this is 1 power. And exactly how they behave like that, that's a bit different story, but let's see. If you went through STEM algebra, certainly you went through that, because that's important there. If you went through either business algebra or algebra for teachers, then you probably went through the end result, formula solution, and didn't really go through the theory. So here, I'm going to take the latter approach. Just remember, crossing odd multiplicity, sign change. Crossing even multiplicity, keep the same sign. And the analogy is -1 to the odd power versus -1 to the even power. Let's apply a similar idea to a little bit harder problem like this. So we have 3 factors now. X equal to -3, x equals to 0, and x equals to positive 2, excuse me. Those are the zeros. Is that clear? with multiplicities 2, 3, and 1 respectively. Nothing is here, so 1 is hidden. So we have odd, even, odd. Is that right? No, multiplicity 2. Even, odd, odd. Sorry about that. 2, 3, 3. So even, odd, odd. So even, odd, odd. At -3, 0, and 2. And some color coding is there as well. I'm representing odd multiplicity as red and even multiplicity in blue. Now, if x value is really, really big, say plug in x is say 1,000 or 100,000, something humongous, so we have positive here. Now, as I cross this odd multiplicity, we have to have sign change, because locally it behaves very much like x minus 2 to the first power times some number. So we have sign change. Now, crossing this odd multiplicity, again, I have sign change. So minus became plus again. Around x equal to 0, it behaves like x to the third power times some number from here to there. So it behaves like a bit of a cubic function around here. So we have sign change. Now, from here, positive, and then crossing this even multiplicity, we keep the same sign, plus hit and bounce back, because around x equal to -2, it behaves like the second power, so quadratic function, times some number. And you want this thing to be positive? Okay, and this diagram, find out positive intervals. Here, positive, another positive. There, no, that's negative. Positive, so we have to take those three intervals. -infinity to -3, -3 to 0, and finally 2 to positive infinity. Here's a graph, by the way. Let's see. Let me copy and paste so that you can see the behavior with this function and the diagram and this graph all together in the same viewing window. Let's see. Around x equal to 2 here, behave very much like a line. It is cutting through because it's 1 power, and plugging x is pretty close to 2. Plugging x equal to 2 there, so it's basically a linear function. Now, around x equal to 0, it behaves like a cubic function. X to the third power here, and plug in x equals to, well, this number is 0, so we get a number there, we get another number there. So it behaves kind of like a cubic function times a certain number. Now, around here, behaves like a quadratic function, hits 0 and bouncing back. That's because around this 0, it behaved like this function, which is parabola, quadratic function, times plug in some number, -3 to be precise. And that's going to be very similar to this guy over here. And that's a theoretical explanation why we end up with even multiplicity plus remains plus after hitting and bouncing back. For odd multiplicity, we have graph crossing the axis and going to the other side. So basically, the local behavior is behaving like an even power function around here, an odd power function around here. That too is an odd power function. Now, if you didn't understand all those theories, still it's okay if you remember the scheme. In the number line, get the diagram. You don't really have to draw everything up to scale, even though I did it here. And then start with positive in the right-hand side, because when x value is sufficiently large, everything will be well positive, unless, of course, the leading coefficient is negative. In that case, you have to start from the negative. And then, each time you cross an odd multiplicity, sign change. Crossing odd multiplicity, sign change. Crossing even multiplicity, same sign. Crossing even multiplicity, same sign. It repeat, and then in the end, you take either plus intervals or minus intervals. This time, I want this thing to be greater than 0, so I'm taking positive intervals. That's the way we do in inequalities.